S. Chan presents educational video lectures as per the new UGC CBCS curriculum. Absolutely free. Difficult science concepts made easy. Study anywhere, anytime.
Hello, we begin today's lecture with a small question. How does organic chemistry relate these following compounds? We have our simple fats and vegetable oils we use every day in our cooking. We have a local anesthetic, lidocaine. Which is commonly given to our teeth when we go for a dental checkup. We have proteins, which are nothing but biopolymers of amino acids. And we have our simple fruits and flowers. Think about it and we'll come back with the answer. I am Dr. Sujata Sengupta. Welcome to the S. Chand Academy. If you want to learn more about today's lecture, then please refer to the book by S. Chand Publishing, the link to which is provided in the drop box below. I hope you have been watching our videos, and especially I hope you have watched our video on the chemistry of carboxylic acid, which is going to be a great help as we continue in today's lecture. I had left you with the question that how did organic chemistry relate all of the following? So now let's reveal our answer. The answer is all of these contain molecules, organic compounds, which are known as carboxylic acid derivatives. For example, our fats and vegetable oils are nothing but triglycerides. What are triglycerides? Triglycerides are ester molecules formed by the reaction of a long chain carboxylic acid with the triol glycerol. Lidocaine, our local anesthetic, and many other anesthetics contain what are known as the amide functionality. Proteins are biopolymers which are consisting of amino acids. How are the amino acids linked together? Yes, again through our amide bond. And plants, they often synthesize esters. Esters will have distinct or characteristic odors that give the special or identifiable smells to many fruits and flowers. For example, our ripe bananas. Where does that distinct smell come from? It comes from an ester known as isoamyl acetate. So, as you see, or as you may have guessed, in today's video we are going to learn all about the chemistry of these carboxylic acid derivatives. Before we begin, what were carboxylic acids? Remember, carboxylic acids were organic molecules which contain the carboxyl group. What was the carboxyl group? When we had the carbonyl group and an hydroxyl group attached to the same carbon atom. These molecules which contain this entire carboxyl group are acidic in nature, and that is why they were known as carboxylic acids. Now, what are these carboxylic acid derivatives? Well, our carboxylic acid derivatives are compounds with functional groups that can be converted to the carboxylic acids by simple acidic or basic hydrolysis. What are some of the most important carboxylic acid derivatives? Well, we can have our acyl halides, we can have our anhydrides, we can have esters and our amides. And so one by one, let's go and look at the chemistry of these acid derivatives. We begin with esters. Esters are carboxylic acid derivatives in which the hydroxyl group of the acid is replaced by another alkoxy group of an alcohol. In other words, esters are the combination of a carboxylic acid with an alcohol with the loss of a molecule of water. How are they prepared? They are commonly prepared by a Fischer esterification reaction, an acid catalyzed reaction between the carboxylic acid and the alcohol. How do we name our esters? Well, the name of the esters contains two parts. The first part or the first word is derived from the alkyl group of the alcohol, and the second word is going to be derived from the carboxylate group of our carboxylic acid. So, let us take a look. Here we have ethyl coming from the alkyl group of the alcohol and ethanoate coming from the carboxylate group of our carboxylic acid. So, overall the name of the ester is ethyl ethanoate, or sometimes very commonly known as ethyl acetate. Here we have phenyl benzoate. So, that was the naming of our esters. Next, we have amides. What are amides? Amides are a composite of a carboxylic acid with an ammonia or an amine. So, when we take our carboxylic acid and it is treated with an amine, it first forms the ammonium carboxylate salt. This, when we heat at high temperature, it undergoes dehydration. So, there is a loss of a molecule of water and it results in the formation of our amide. This is the basic amide functionality. Amides are planar molecules with the carbon-nitrogen bond having a partial double bond character. Why? Yes, because the non-bonding lone pair electrons on nitrogen, it undergoes delocalization and resonance stabilization, and so it has a partial double bond character. The amides can also be classified as being primary, secondary or tertiary depending upon the substitution on the nitrogen atom. A amide which has the general formula of RCONH2 is commonly known as our primary amides. If an alkyl or an aryl group is present on the nitrogen atom, as we have over here, such amides are known as secondary amides. And if we have two alkyl or aryl groups present on the amide, then these are known as our tertiary amides. How do we name our amides? Very easy. First, we name the corresponding acid. Then we drop the ic acid suffix or the oic acid suffix, and instead we add the suffix amide. If we are going to have secondary or tertiary amides, then the alkyl groups that are present on the nitrogen, they are treated as substituents, and generally we specify their position by writing the prefix N. So, here I have an ethyl group on the nitrogen atom. So, this becomes N-ethyl, and the parent acid was ethanoic acid. We will drop the oic acid, add the suffix amide, so it becomes N-ethyl ethanamide. This also has a common name of N-ethyl acetamide. Similarly, here you can see we have two substituents on the nitrogen. So, here it is N,N-dimethyl methanamide, more commonly known as N,N-dimethyl formamide. So, many of the amides also have a common or a trivial name. Acid halides also commonly known as acyl halides. Our acid halides are the most reactive derivatives of the carboxylic acids. And here the hydroxyl group of the carboxylic acid is replaced with a halogen atom. For example, a chlorine in the case of an acid chloride. Why are these the most reactive? Yes, you have guessed it, the electronegative nature of the halogen atoms. It withdraws the electron density, making the carbon of our carbonyl group even more electrophilic. Therefore, it can be very readily attacked by nucleophiles, being more reactive in nature. How do we name our acid chlorides? Very easy. We first take the name of the parent acid. We will drop the ic acid suffix. We add "-ile" followed by the name of the halide. So, here I have ethanoyl chloride, also with a common name of acetyl chloride. Here I have propanoyl chloride, also known as propionyl chloride in its common name. The word anhydride literally means without water. And so, acid anhydrides are those derivatives which are formed by the reaction of two molecules of carboxylic acids with the loss of a molecule of water. Our anhydrides are also far more reactive than our simple carboxylic acids, but they are not as reactive as our acid chlorides. How do we name our anhydrides? Very easy. We will simply take the name of the parent acid, but we will change the word acid to the word anhydride. So, here we have ethanoic anhydride coming from ethanoic acid, also commonly known as acetic anhydride, and here we have 1,2-benzene dicarboxylic acid, which you will notice from its structure, it has a common name known as phthalic anhydride. What are some general properties of these acid derivatives? Well, these acid derivatives, they tend to be polar. They are also soluble in most organic solvents like alcohols, ether, even aromatic hydrocarbons. And most importantly, some of these acid derivatives themselves are used as solvents in various organic reactions. For example, our ester, common ester ethyl acetate, is an excellent moderately polar solvent with a boiling point of 77 degrees, very commonly used in the organic laboratory. Molecules like acetonitrile, dimethylformamide are extremely polar in nature and also serve as excellent highly polar solvents, almost comparable in its polarity to that of water. Moving on, let us look at the reactions of these carboxylic acid derivatives. Perhaps the most important reactions of these carboxylic acid derivatives is that they can undergo reactions with a variety of nucleophilic reagents, both under basic and acidic conditions. These reactions are commonly known as a nucleophilic acyl substitution. So, here for example, we have our simple or a general carboxylic acid derivative and we have our nucleophile. How does the reaction takes place? Here you can see in the first step, the nucleophile will attack the electrophilic carbon in the carbonyl group of the acid derivative. Once it does that, it leads to the formation of a tetrahedral intermediate. So, let us draw this. Next, we will have the loss of our leaving group and the reformation of our carbonyl moiety. Alright, so this is the basic mechanism of a nucleophilic acyl substitution. So, these reactions are also known as acyl transfer reactions. Why? Because we are transferring the acyl group from our leaving group to our nucleophile. And overall, you can see that this mechanism, it involved first an addition reaction followed by an elimination reaction. Remember, all nucleophilic acyl substitutions will follow this basic addition elimination mechanism. Now, I will leave you with a quick question. Do you think all acid derivatives have the same reactivity towards nucleophilic acyl substitution? Think on it and we'll meet after the break.
Hi, I'm Manika and you're watching Chand Academy. I'll be discussing the topics like carbohydrates, amino acids, peptides, proteins and many other topics related to BSc program. For more such lecture, you can stay tuned to our channel and subscribe to our videos so that you get more and more info about our upcoming lectures. You can also refer to our previous lectures on the related topics. Stay tuned, stay focused because it may help you in your competitive exams also and preparation of the other topics also related to your courses. Thank you.
Welcome back to the Chand Academy. Before we left for the break, I had asked you a quick question. Do you think all the carboxylic acid derivatives will have the same reactivity? No, they don't. Certain acid derivatives are more reactive than that of other acid derivatives. So, what factors are responsible for this difference in reactivity towards this nucleophilic acyl substitution? The reactivity, it depends upon not only the structure of the acid derivative, but it also depends upon the nature of our attacking nucleophile. More importantly, it also depends upon the nature of our leaving group, that X molecule. Remember, weaker the base, the better is the leaving group. And so, our acid chlorides, where it is the chlorine atom which leaves as the Cl minus, is going to be most reactive in terms of reactivity of the acid derivatives. Our amides, remember, they underwent a resonance stabilization leading to a decreased reactivity. And remember that the more reactive acid derivatives are easily converted into the less reactive derivative. So, here you can see that our most reactive acid derivatives, the acid chlorides, can readily be converted to the anhydrides, the esters, the amides. Our anhydrides can be converted to the esters, the amides. Esters, on the other hand, can be converted to the amides or carboxylic acids upon hydrolysis, whereas our least reactive amides can only be converted to the corresponding carboxylic acid upon hydrolysis in acidic conditions, or to the sodium salt of the carboxylic acid if we treat it with a base like sodium hydroxide. So, here remember that the more reactive acid derivatives are easily converted into the less reactive acid derivatives. before we move on, let's look at the simplest and one of the best examples of a nucleophilic acyl substitution, and that is a reaction that is known as transesterification. Esters readily undergo transesterification. What happens in this reaction? Here, one alkoxy group in the ester, it substitutes for another, either in the acidic or basic conditions. So, in other words, it is nothing but the interchange of the alkoxy group of two alcohols. This transesterification reaction, it can occur both under acidic and basic conditions. So, for example, ethyl benzoate will undergo reaction in methanol in the presence of acids like sulfuric acid to give us the methyl benzoate followed by ethanol. This acid catalyzed transesterification reactions is actually an equilibrium reaction, and so the reaction is carried out in the presence of excess of ethanol to drive the reaction to the forward direction. In the base catalyzed transesterification reaction, our ethyl benzoate is treated with an excess of sodium methoxide in methanol to give us methyl benzoate and ethanol. How does this happen? Let's quickly take a look. So, in the first step, our strong nucleophile, the methoxide, it attacks the electrophilic carbon of our ester molecule. And when it does that, it first forms our tetrahedral intermediate. In our next step, we are going to have the reformation of the carbonyl group with the loss of this ethoxide molecule. And so, we have our simple transesterification reaction where ethyl benzoate is converted to the methyl benzoate. This was under our basic conditions. Let's quickly move on to some of the chemistry of these carboxylic acid derivatives. We begin with the chemistry of our acid chlorides. The acid chlorides, how are they formed? They are formed very readily in the laboratories by treating the carboxylic acids with either thionyl chloride or even with oxalyl chloride. Acid chlorides, remember, or acid halides, these were the most reactive among all the carboxylic acid derivatives, and so they can be hydrolyzed to the acid. They can be treated with an alcohol to give the esters. They can be treated with amines to give amides, and they can even be treated with carboxylic acids to give us the anhydrides. Now, the chemistry of anhydrides. So, similar to the acid chlorides, anhydrides are also slightly more reactive acid derivatives, but not so much as our acid chlorides. Acetic anhydride is the most common anhydride. Certain anhydrides, for example, like our cyclic anhydrides, can easily be prepared by simply heating, which is very commonly done in the lab for the synthesis, for example, of phthalic anhydride or succinic anhydride. Otherwise, the general method for making anhydrides is either by the reaction of an acid chloride with a carboxylic acid. And The most important reaction of our anhydrides is that they undergo nucleophilic acyl substitution, and so they serve as very good acylating reagents. So, here you have the Friedel-Crafts acylation reaction. Another important reactions of the anhydrides is known as the Perkin reaction or the Perkin condensation. What is this? This is an organic reaction which is very commonly used for the synthesis of alpha beta unsaturated carboxylic acids. Here it involves the condensation of an aromatic aldehyde with the anhydride in the presence of the alkali salt of the carboxylic acid, which acts as the weak base. These reactions, which was developed by William Perkin, is typically used to make cinnamic acid and its derivatives. Esters, as we know, are very common constituents of various plant oils. They have characteristics aroma. How are they prepared? Esters, you will remember, are prepared by the Fischer esterification reaction, an acid catalyzed reaction between a carboxylic acid and an alcohol. Esters are very commonly used for reactions where it can undergo hydrolysis under acidic or basic conditions to give us the corresponding acids. This was something that we had discussed in our previous video in the S. Chand Academy in the chemistry of carboxylic acids. We had previously also discussed in this video about the transesterification reaction, where the alkoxy group of the ester is substituted by the alkoxy group of another alcohol. Esters can be reduced by hydride reducing agents like lithium aluminum hydride to the primary alcohols, and esters, if you remember, also reacts with two molecules of our Grignard's reagents to give us tertiary alcohols. Again, both these reactions we had discussed in details in our video on the chemistry of alcohols. One important reactions of esters is known as the Reformetsky reaction. Here it is an organic reaction that helps to convert a ketone or an aldehyde and an alpha halo ester to a beta hydroxy ester in the presence of metallic zinc followed by an acidic workup. So, the reaction works best whenever we use inert solvents, for example, like tetrahydrofuran. And the reaction, it only takes place when we are going to be using zinc. And in the reaction, first our alpha halo ester, it reacts with zinc to form the zinc enolate. Okay. This zinc enolate then attacks our aldehyde or a ketone to form the addition product. Which on acidic workup is now going to produce our beta hydroxy ester. Finally, amides, as you remember, these are the least reactive acid derivatives. And how are they synthesized? Amides are typically synthesized by the reaction of an acid chloride with that of an amine. And since the amides are so stable or least reactive, so the only reaction that it typically undergoes in terms of nucleophilic acyl substitution is hydrolysis to the corresponding carboxylic acid, either under acidic or basic conditions. Amides can also be reduced with hydride reducing agents like lithium aluminum hydride to synthesize the corresponding amides. With that, we come to the end of this video on the chemistry of the carboxylic acid derivatives. I hope you have enjoyed the video and have learned a lot on the chemistry of these acid derivatives. You can always refer to the book by S. Chand Publishing, the link which is provided in the drop box below. If you've enjoyed this video, then please do hit the like, share and subscribe button, and don't forget to hit the bell icon to stay tuned for further videos. Thank you.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.